Thank you so much for this introduction. I'm really happy to be here at FLAPS and to have the chance to present my work. So my work is about simulation tools for beyond CMOS devices based on unconventional materials. And in particular, I will speak about vanadium dioxide for application in neuromorphic circuits. So this is the outline of my talk. I will start by introducing the envisioned field of application, which is edge computing. For this particular kind of neuromorphic circuits, which are called oscillatory neural networks. Oscillatory neural networks are essentially systems of coupled oscillators. And as you can imagine, the elemental brick is the oscillator. Now, CMOS technology, in order to, if you want to implement an oscillator with common CMOS technology, usually you need to have a complex circuit, like complex meaning organize a set of at least tens transistors. But there are also ways to implement oscillator in very compact way using, for instance, materials like vanadium dioxide. In particular, with just one single device based on a two-terminal device, so a quite simple architecture, you can implement, I will show you how, a very compact oscillator. And this means that this is a great advantage for the scalability of the circuit. And why this is possible? Because there is this mechanism called resistive switching in vanadium dioxide that I will explain. And my work, as I mentioned before, is in particular about simulation. So I will show how it has been implemented, a TCAD approach, technology computer-aided design approach, in order to model this resistive switching of vanadium dioxide. Now, TCAD is a common technique that has been used in the semiconductor industry and has already been very successful in assisting the development of silicon technology. And it's becoming more and more important now because the technology is dealing with material with exotic properties, so unconventional material compared to silicon, and also new device concepts. I will show how this approach has been, I have used this approach in order to investigate some issue related to some feature of the device, like for instance, how to increase the power efficiency of the oscillator, and also through a linked technique called the TCAD mixed mode, is possible to scale from the device to the circuit, and so to have also an assessment of the dynamics of the circuit, which is quite important because neuromorphic computing is an analog computing approach, which means that it's the dynamic of the circuit, the physical dynamic of the circuit, which yield the output of the computation. So, about edge computing, edge devices are connected together and they form the so-called Internet of Things, IoT ecosystem. Usually they collect through the sensor, the data locally, and when there is it is required an intelligent analysis, the data are sent through the internet to the cloud, so ensemble of cloud data centers. But this is becoming increasingly unsuitable because of the issue like, for instance, limitation of bandwidth, security, and also latency. So the trend is to bring AI at the edge, which means to process the data locally where they are collected. But this has some challenge, brings some challenge, because as you can imagine, there are differences in resources for cloud data center compared to edge devices. In particular, the power is, the access to power supply is limited in edge devices due to the shrinking dimension of the devices. That's why it's important to investigate approaches for computing, which works with the low power consumption. But current traditional computing machines are based on von Neumann architecture, which means separation between memory and processor. Because of this separation, during the processing of data, there is a lot of traffic, and this traffic is huge power consuming. So there is a need to overcome the common, let's say, the traditional von Neumann computing paradigm and to search for new computing paradigm. A possible solution is neuromorphic computing. Why? Because the human brain, as shown, that it is possible to perform very sophisticated tasks with very low power consumption. And basically, the human brain is composed by, in very simplified, a very simplified description of a human brain is an ensemble system of neurons, which are connected together through synapses. And many kinds of neurons can be modeled as oscillators. That has brought the idea to mimic the activity of the brain through systems of coupled oscillators or oscillatory neural networks. Now here I'm describing I'm giving you a survey how it works when as a computing machine. So the information in ONN is encoded in phase difference. In the beginning, all the oscillators are uncoupled, and they are initialized by biasing with the given delay time. This introduces a phase difference between each oscillator and a reference oscillator. Then at a certain time, you couple all the oscillators together. They start to interact, and after a certain time, if any, a synchronization state is achieved. Such a synchronization state is the outcome of the computation. As an easy example of application, you can imagine to apply ONN, for instance, for image recognition, because you can think to map the phase difference, for instance, to a color gray scale. So this allows you to map directly the phase difference during the dynamics of the ONN with the color of the image. As I mentioned before, this is an analog computing paradigm, which means the dynamics of the system is really important. I mean, it gives you the working of the machine. That's why it's important to have a robust design methodology in order to understand, for instance, the link between the material and device architecture and also the circuit dynamics. So in particular, in this talk, I will focus on, as I mentioned, TCAD, which means device simulation, and also TCAD mixed mode, which allows you to access the circuit simulation with a very and quite accurate description of the device physics. So this is in a nutshell what is TCAD and TCAD mixed mode. So TCAD is a semi-classical transport approach, drift diffusion, based on drift diffusion. As a rule of thumb, it works for systems whose size is between 100 nanometer up to 100 of micron. And in TCAD, what happens is you essentially solve self-consistently Poisson equation, current equation, and continuity equation. And you have also the availability of many physical models, for instance, to describe the strain of the material, or for instance, the thermal properties of the material. And you solve the device physics in a geometry, in a mesh, which accurately reproduce the geometry of your device, which is quite important, for instance, if you need to have an accurate description of electrostatic, or for instance, for a thermal behavior. Then TCAD mixed mode, it means to solve the equation of a circuit, not using what is commonly used, which means compact models. So essentially you have analytical formula which describe you the behavior of the device, but at each step you solve the circuit equation, and then you solve at this step also the device, you perform device simulation. So you don't have, let's say, a behavioral, a simple description, an analytical description, but you really made a simulation at each step of the circuit, which yields you the most accurate possibility to assess how the device behavior is impacting on the circuit dynamics. So to introduce the vanadium dioxide is the transition metal oxide, and it has many important characteristics, property, but the most important, at least for the application that I'm showing, is the possibility to make a transition from insulator to metal. So there is a change of structure, and this is triggered by temperature, and this brings the so-called resistive switching, which means a change in the resistance, even of order of magnitude. So what happens is usually that you start in the insulator state, then the temperature is increased, usually at a given threshold temperature, which is around 340 Kelvin. It happens with transition, and so you have a resistivity drops, and because the material becomes almost metallic, bad metal, let's say. The important thing is that this resistive switching is volatile, which means that the change is not permanent. So differently from what happens for non-volatile membrane, what happens here is that when the material cools back, you naturally go back to the original insulator state. So in the first case, you speak about insulator to metal transition. In the second case, it is called metal to insulator transition. And what is important is that the same resistive switching, it has been observed not only triggered by external temperature, so when you provide the temperature externally, for instance, through an heater or by the change of external temperature, by changing the ambient temperature, but also in the channel of two-terminal devices, when voltage is applied across the contact or by current injection. And in this case, there is debate about what is the exact mechanism, but what is thought, there are experimental evidences that points toward the role of Joule effect, so self-heating, by regulating, by contributing an increase or a decrease of temperature inside the device as the main mechanism triggering the resistive switching in VO2 devices. As I mentioned, this is quite important. This is an important property for the implementation of a compact oscillator. Because this resistive switching brings you a characteristic S-shaped curve for the current versus voltage across the device characteristic. This S-shaped curve is associated to the appearance at a certain point of this region of so-called negative differential resistance. So the slope becomes negative. And then if you insert the two-terminal device into a simple RC circuit, and the parameters of your circuit, in particular VDD, so the voltage, and Rx, the external resistance, is such that the associated load line cross the negative differential resistance region, then you know that your circuit at the output node would yield an oscillatory signal. So you have realized, as I mentioned in the beginning, a very compact and scalable oscillator, essentially just using one device. So how to model in TCAD vanadium dioxide resistive switching? This has been implemented by a partner, Silvaco, in the NeuroMorphic project in which I'm currently working. So they treated vanadium dioxide as a resistor network. And in particular, they modeled in Silvaco, in TCAD Silvaco, vanadium dioxide is modeled as a conductor. And the resistivity of this conductor is made local dependent from the temperature. This has been achieved by customizing an already available model, the so-called PCM model for the resistivity. And so when I have to perform my simulation, essentially I do 3D electrothermal simulation, which means that I solve self-consistently Poisson equation, heat equation, with the heat equation. And in heat equation, the heat generation rate is associated to the electrical power. So it's the contribution given by the Joule effect. The TCAD simulation gives you also the possibility, for instance, to take into account the thermal boundary condition, which are quite important because when you want to capture correctly the thermal behavior. So for instance, in this case, what I set is the heat flux at the thermal contact. In my case, as you will see, the thermal contact is the interface between the vanadium dioxide and the substrate, because this is thought to play the major role in the heat dissipation. And you have this parameter, which is the thermal conductance, which in fact regulates the heat dissipation at the thermal boundary condition. So here is the kind of device that I have simulated. This has been fabricated by another partner of the NeuroMorphic project, IBM. It is in the so-called crossbar configuration. So you have a top and a bottom electrode, and they sandwich the vanadium dioxide layer. And this crossbar configuration has been thought in order to achieve a better control over the switching region, because of course, in this case, most of the current is flowing across the overlapping region of between the two electrodes. And what has been experimentally demonstrated is that compared to the more common planar geometry, this configuration allows to have devices with larger repeatability and reliability, which is important in order, especially working with the oscillators. And so this is the full flow, of course, that it's preliminary for a simulation. So calibrate and validated of the TCAD model. So starting from resistance versus temperature measurements, I have used this to calibrate the PCI model, so the resistivity model, and then I have, how to say, benchmarked my current versus voltage simulation against experimental data. And this has been useful for me to understand if I achieved a good description then of the device behavior, but also as a means to fine-tune some parameters which are not easily accessible experimentally, like for instance, the interface thermal resistance or thermal conductance. So here are some results that I've got by the approach that I have just illustrated. In this case, I have investigated the size of vanadium dioxide, keeping the same contact width. You can, I mean, because I told you before that the current is flowing in the central region of the device, you can think that this is the active area, but the dimension, the size of the vanadium dioxide has an impact, especially a thermal impact. You can see here, for instance, the effect of varying the dimension of the vanadium dioxide. I repeat, keeping constant the contact width for VAV. So there is a shrinkage. That means that the device is turning on, the transition is turning on at lower and lower applied voltage. And this mirror in a trend for the so-called EMT and midpoints. So at the points in which you have the switching and there is and the switching back from insulator to metal and from metal to insulator. And I mean, this is important because, as I mentioned before, the negative differential resistance region is essentially individuated by these points. So that means that also this negative differential resistance region is varying with the size of the vanadium dioxide layer. And in particular, you have like the condition in order, which is the minimum VDD and external resistance that you can apply in order to have oscillation. You can individuate because the load line is that gives you these values is the one passing through the EMT and midpoints. And so you see in the plot on your right that the trend is of decreasing, for instance, of VDD with the decrease of the size of the vanadium dioxide. And also, if by applying, I mean, by performing simulation applying this load line, I could have an access, an important information regarding the power regarding the power consumption, and in particular to determine the average power per cycle. And again, I got this trend of decrease with decreasing the size of the device. Another kind of investigation that I have performed is, for instance, the effect of the interface thermal resistance, so the thermal conductance, which is material property, okay, over vanadium dioxide oscillator. In this case, I have investigated two different kinds of load lines. As before, the load line that is passing through the two EMT and midpoints, which give me the load line with the minimum VDD for which I can get the oscillation. So it's like the minimum VDD that you can apply in order to get your circuit to work as an oscillator, but also another kind of load line that I labeled as load line B, which is the load line passing through the central region of the negative differential resistance region. This is, it's a higher power. This load line individuates higher value of VDD, but at the same time allows you to work in a more stable region. So in both cases, what I got, and you can see in the plot in the bottom, is again a trend of decrease of the power with the increase of the interface thermal resistance, or with the decrease of the thermal conductance. And as a last example of possible application of the simulation tools, as I mentioned, the application of the TCAD mixed mode. So in this case, I am simulating a system of a coupled oscillator, which is the simplest ONN circuit that you can imagine. And as a coupling element, I have used a simple resistance. And in the two, on these two plots that you under the circuit schematics, you can see an example of the working of this device. So in the beginning, you have the two oscillators that are uncoupled, and they are initialized with the given phase difference by biasing with the delay time one oscillator compared to the other. Then at a T-switch, you couple the system and start the settling phase. And after, because the oscillator starts to interact, and after a while, which depends from various conditions, you get, if any, a synchronization state. In this case, you can see an example of an in-phase and out-of-phase synchronization state. And on the plot on your right, you can see that what I did is to plot, to map different delay times and different resistance value in order to get an idea of what is the possible outcome of the circuit, out of phase and or in phase, which is important for application of ONN as a computing engine. So here I have just listed some publication where you can find more detail on ONN and also on TCAD simulation tools applied to this kind of to simulate some vanadium dioxide devices, oscillators, and also ONN circuits. And so these are my conclusions. So I have shown an approach performed by TCAD in order to simulate a resistive switching in vanadium dioxide, but of course it can be generalized to any transition metal oxide material based on this particular mechanism of resistive switching, which is the insulator to metal transition. And I have shown how this this provides you the possibility to build a simulation tool chain, starting from the device, cleaning up to a circuit based on such devices in order to assess the circuit dynamics to be applied for neuromorphic computing. And I have shown that the TCAD approach has been calibrated and validated successfully. And I have applied this approach in order, in particular, to investigate how to increase the power efficiency of the device, which is a topic quite of interest nowadays, because both from the economic point of view, like also from the environmental point of view, we need devices which are working with low energy intake. And also I have shown you how this approach can be scaled up and used to assess the dynamics of this kind of circuits. So finally, let me acknowledge the project coordinator of Neuron and my postdoc supervisor, which is Dr. Aida Todri-Sanial, the team members, the LIRMM, the CNRS, the University of Montpellier, the partners in Horizon 2020 Neuron project from Silvacom and from IBM. And this is all from my side. I thank you for your attention. And if you have any question, I will be very happy to answer.